section 3.9, we're talking about derivatives of exponential and logarithmic functions. We will start with the derivative of e to the x. We don't need the sounds for dramatic effect. So we'll start with the stuff you already know, which is the derivative of e to the x is e to the x. And you know already from implicit differentiation that derivative of e to the y in respect to x is e to the y, and then followed with the chain rule dy dx. So I can rewrite the chain rule in more, I guess, user-friendly form by writing it this way: e to the f of x. If I write e to the f of x, then I have ability to plug in any function there. So we can take derivative of e to the x squared. We can take derivative of e to the sine x, e to the tangent x. We can do any of those combinations. And that will be, again, right, Control C, Control V, right? You take the entire e to the f of x and you copy it. And then you multiply that by the derivative of the function, which is technically that dy dx chain. And I will lightly box this one, because this is what you are actually going to use most of the time when you see e to the x, because it's usually not e to the x, it's e to the some little variation of x. Most of the time, especially in differential equations, you're going to see e to the 2x, e to the negative 5x, and so on. So you want to remember this one. And we understand that exponential functions allow for any base. So e is the special one. E is the special one. But we can have any base there. You can have 2 to the x. You can have 3 to the sine x. So technically, the most general case that you can have is a, which means any number under the sun raised to a function. So this would be the most general case that you can get. So now it will again start with Control C, Control V. The derivative is, again, a to the f of x. So as is, but this time times ln a, and then times f prime of x, which is the chain rule. So these are the two things that are happening. And this is the one that I'm actually going to box, because this is the one that actually is the general case. So now I'm going to make the comparison between first these two. I'm going to say, you can clearly see that if a is e, if a is equal to e, right, then you get this formula above. Because as soon as you put e for a, you still get e to the f of x, and then ln e. ln e is 1, right? And you still have times f of x. So that's that jump. And you can obviously have this jump here by saying that a is equal to e and f of x is x, in which case you get the first formula we ever learned. So this is the most general case for our exponential functions. So let's work on 3 examples and then move on and do the logs, because logs are the ones that are interesting and fun. So what is the derivative of e to the negative cosine x? Yes. Yes. So we will copy the same thing and then multiply by the derivative of the exponent, which is negative sine x, so it's just sine x. So if you want to write it, well, it doesn't matter. It's the same either way. Sine x times e to the negative cosine x. That's great. Perfect. How about the derivative of x squared e to the minus 5x? Which method do we have to use? Product rule. See? This is what I like. Enthusiasm on Saturday morning. Product rule. With a smile, yes.
Negative 5x squared e to the negative 5x plus x e to the negative 5x.
Awesome. So, copy the first one times the derivative of the... No, copy the first one and copy the second one. Wow. Copy the first one. There we go. Derivative of the second one. And then plus copy the second one times the derivative of the first one. And now, I did mention this before, factor it as much as possible. As much as possible. So you see that both have x and e to the negative 5x. So we have what? 2 minus 5x. And guys, this is going to be your question in 4.1, except now you have to say equal to 0 and then do the rest of the problem. So this is why, you know, it builds up. So 4.1, 4.2, 4.3 will all have this exact problem. And once you find the derivative, you go equal to 0, figure out what x's are making the equation 0, and then you can do other stuff. So practice factoring now, when it's the only thing you have to worry about. Let's do one more example, because we can. How about 2 to the x sine x is good? All right. Right there. Can't miss. See if you are squinting. So I don't want you to miss out on this opportunity. Wonderful opportunity. Log 2, okay, and then what else? Okay. That's it? I know. It's like magic. You want? No, you don't want? No, she's angry. She doesn't want to. She's really angry. I can see you angry. You are very angry. You're so angry that I might leave because I'm uncomfortable. What happened?
Just like last week when we were just going in the hallway, you wanted to leave.
Oh yeah, that was very dangerous. That was very dangerous.
It's not safe, yeah. This has to be safe environment. Outdoors, that's what I want to be happy. Happy, happy. Happy. Okay, some people are not. Or mine will be happy. Or about to be happy. Trying to hold it. Look like they're not happy. Yeah, they look like it. I actually want to like it. This is what it is. Like there is a kid in Malaysia sewing, alright, sewing a coat that someone is gonna buy for $300, right? For a meal. For a rice meal. One meal a day. Like the music to get even healthy. I know that life. Have you worked out the US? Depressing, right? Very depressing. I know. And you find out again. You can also check out your mental state. Because that's the conference you go only once as a student to, and then forget, like, screw it, I'm not going anymore. But you have to go to therapy after that. Good. Well, maybe she doesn't hear from that. Then you're going to get depressed. It's a rotary conference. So Rotary was Congress. You have to break out the second part. What do you think? No, cosine to sine is negative, sine to cosine.
Okay, let's take a look at this problem together. Ready? I'm going to mix it in. So we will be using this formula, the general case, because we have 2 to the function rather than e. So we copy function as is. We multiply by the ln of the base, and then we multiply by the derivative of the exponent, which is product rule. So we have to suffer a little bit there. Copy the first times derivative of the second, plus copy the second, and then derivative of the first, which is derivative of x is 1. So we're done.
Something else with that, right?
I'm sorry? That's it. You were disappointed?
Yeah, I thought it was more than that. I don't know why.
Want another example? So much eager. That's great. Let's do another example. No, this is great. Let's do 5 this time. Bless you. You are okay? Um, let's see. How about cosine 4x divided by x squared plus 1? There we go. Oh, right on time. You don't want to miss this party. All right, so what do we do with this? quotient rule at the end. Very good. So we have 5. Oops. Pen glitched. 5 cosine to the 4x divided by x squared plus 1. And then we have ln 5. I hope you didn't forget that one. And then we have quotient rule. Now, did you catch the little chain rule that I peppered in? Yeah, you did, right? Good. So we take the, I know I'm horrible, x squared plus 1, and then derivative of the cosine to the 4x, which is negative sine 4x, and this is times 4, right? So we have to put times 4. And then minus cosine 4x times 2x divided by x squared plus 1, everything squared. Awesome. So there was that one thing. Usually what I see on exams is you would probably forget the 4 or worse, ln 5 right there, right? Don't forget ln 5. It's not there for decoration, right?
Why is that 4 there?
It's a chain rule because the derivative of cosine is sine, but the derivative of cosine 4x is the sine 4x times 4. This is chain rule within the chain rule. Oh, yeah. The main function is 5 to the function. So the fact that we're doing the ln 5 and therefore the chain. Otherwise, we don't need to be x. Actually, it's not equal to x, it's some form of x. Depends only on how severe. So do we have at least 2 people happy? Okay.
Yeah, I'm happy.
How are they happy? She's still angry? Okay. Are we ready for logs? Yes. Apparently no. So now we're going to do the second half. Well, actually, no, this is the second third of the lecture because the third would be the logarithmic differentiation. Before I talk about logs, derivatives of logarithmic functions, I want to just have a brief introduction into logarithms because a lot of people are really afraid or never actually learned anything about logarithms. Because they looked strange, I guess. I don't know. But let's just put that all behind us, looking at how much is 2 plus 3? 5. And look what I can do. 5 minus 3 is, and 5 minus 2 is. So there was this operation opposite to addition, which could recover both 2 and 3. How much is 2 times 3? So how much is 6 divided by 2? And how much is 6 divided by 3? Awesome. So again, there is the opposite operation which can recover both of the factors, 2 and 3. All right? 2 cubed is equal to 8. So cube root of 8 is 2. How do I recover 3? Yeah, that's the missing piece. Here, I'll write it in blood. Nothing special. It's mathematical operation, like adding or subtracting or multiplying. That's what logs are. Why it look weird? Because it's letters. If they came up with some kind of fancy, cute symbol, I don't think it would be as threatening as 3 letters, right? As the operation. So I don't know. Figure out anything in between. It would be I guess, easier. So log is not a function. Logarithm is not a function. Logarithm is operation that you can do between two numbers to compute. So you combine numbers with addition, subtraction, multiplication, division. You can square, you can cube, you can take a cube root, and you can also do log. Logarithm is mathematical operation just as addition is. So once we clear that out of the way, the next thing is, well, what do we do? Can we make the function with the log? And the answer is yes. Because in order for me to create a function with addition, I will take either 2 or 3 and replace it with x. And as soon as I have x plus 3, right, equals to some kind of y, you have a function there. If I go to either multiplication or division, it doesn't matter. Let's go with division. If I go 6 divided by x, right, instead of 6 divided by 2, I go 6 divided by x. And I say y equals to that. It's a function. Also, I can make exponential function by saying 2 to the x. And finally, I can do the log function like this, log 2 of x. So logarithm is not inherently a function. It is mathematical operation just like addition or subtraction or whatever else, which can be casted into a function by introducing a variable within that log. So over here we have a linear function, and we have a rational function, and we have exponential function, and then we have a logarithmic function. So understand that at the base that logarithms are ways of computing, which are different than anything else, obviously. And I guess that just because you learn it so late in the mathematical career, that's the reason why they're threatening. Because you technically take care of all of the operations by what, 4th, 5th grade, right? And then you wait another 4 or 5 grades before you see log as the operation. I believe that if you took care of the log immediately in the 5th grade, it would not be any different than addition or subtraction. So don't look at the log, and don't discriminate, okay? Be nice, all right? Logs are people too. All right, so now, properties of logs. So every single one of these mathematical operations has properties. You have, for instance, that addition is commutative. You can swap the spots of 2 and 3, and the answer is still 5. You can distribute. There is associated property for it as well. Then between addition and multiplication, you have distribution. So there are a lot of these properties that you can learn in algebra. Well, there are 3 properties that you should learn for logs. And if you know those properties, you technically, and then 2 what I call cute rules, you technically know everything that you need to know about logs. So I'm going to list those. So log of any base of x times y, log of any base x times y is equal to log ax plus log ay. So if you have, by the way, this is called an argument of the log. Argument. Whatever is there after the log is called the argument. So the multiplication in the argument turns into addition of logs. We have another rule which says log a x over y, and by common sense that would be what? Minus sign. Very good. And the third one is the power rule. So log a of x to some power p is p log base a of x. Great. These are the 3 rules that you must know. And you will see that for that differentiation technique that I want to teach you, and those of you who want to, you will learn it. You must know these, better than a palm of your hand. Cute rules. log any base of 1 is always 0, and log any base a of a is always 1. I call those cute rules, but there are rules of logs as well. You can just, you know these. And it's so difficult, a great exam, and you just see, because you have the basic calculator and leaves ln1. That's good. Right, 0. Now we get to that part where I say that ln is a special base, right? Base z. So we just have a different notation for it because we're lazy, okay? You will find that any log out there is spelled out other than 2 log bases that are frequently used in sciences. So you will always spell out log 2 of 10 or log 7 of x. You will always spell those out. But if you have log base c of x, you will abbreviate that by ln x. Call it natural logarithmic function. And the reason is that most of the stuff in nature is based on e. So those decay problems and population problems, there's a lot of stuff that is modeled and it just uses e as a base. So anytime you see ln x means the base is z, and literally just understand it this way, it's a lazy notation. This has 5 characters, this has 3. That's it to it. Nothing special, all right? Nothing special. So all of these rules, you can just replace these 4 characters with a single ln, right? So ln, they all hold because a is e in that case, and a could be e, could be 3, could be 7, and could be also e. So if it's e, we have the short version, and then you also have one that frequently appears in physics and chemistry, which is log base 10. And we just, yes, for pH calculations, very good. So log base 10 of x, the lazy notation is just log x. Again, 2 characters shorter, you don't write the 10. So if there is no base, you just write log, and it's understood that it's base 10. So now if you look at your TI-83 calculators, there you go, TI-84, you will only find 2 buttons there. You will find capital ln and capital log in the left column. So that's base C and base 10. All other bases you can convert into. And technically, the more sophisticated the calculator or the software tool is, the less log buttons it has. So you are going to find calculators which allow you to type in any log with any base and any number. And I believe those are those calculators, like a scientific one. I think they allow you to do all of that. They're not graphing. You're jumping on a graphing, which is, again, higher functionality than the scientific one, because it has everything that scientific doesn't, because you can't put the log. They only offer these 2 choices. When you go to Mathematica, you only have 1 choice. And that's this one. But the confusing thing as hell is that they write it this way. So every time you see on Wolfram Alpha in Mathematica, you see log, it's actually base C. So that's the confusing part, but, you know, such is life. So in engineering, you will only consider, the only one that you consider in engineering is base C, so that's why I don't care about anything else. But for purposes of physics and chemistry, right, the pH calculations, for instance, you will need to know log base 10. In physics, the Richter scale for earthquakes, and then talking about the decibel scale for sound, like strength of the sound, talk about intensity, all these things, you will be using log base 10 calculation. So they're around as well. Now, what happens if you are supposed to compute log base 2 in a calculator and you don't have capability to do that? Well, you can simply use the change of base formula. And change of base will take log 2 of 10 and write it as, let's say, ln 10 over ln 2. And you can figure out the rest on your own. All right? So change of base formula will easily convert into anything. You can also use LOG instead of. So this was the review of actually everything you learned in Precalculus regarding logs. That's it. There's nothing else to add to this story. You know now 100%. You can go review, can rewatch the stream. Hopefully it's going. Let's see. Yep, it's live. So you can rewatch the stream how many times. And I will be teaching this because I'm also streaming Precalculus 1. There will be a full lecture in about a month and a half. Full lecture on these logs there. So you will have it for reference. Calc 2 is coming, right? Should I say winter is coming? So, yeah. So that and trig. Trig. That's Calc 2. Trig. Guess the drift? See, a little bit of trig. And then some other sines and cosines, a little bit peppering like some cotangents here and there. A little bit more stuff. See? Trig. So this is where your winter break is gonna melt if you're taking Calc 2. Just grinding to, and here's the next section. This is the problem. Looks like this, right? Just x's and square roots, and it's awesome. And the first thing you do is you take that and you make it into this because it's easier. So yeah, keep reviewing stuff for that course, and I will give detailed instructions of what exactly is what you need to survive, and hopefully you will do that stuff review that stuff over the winter break. So the Calc 2 is much easier in that case. Otherwise, it's hell on earth. We're talking fires and brimstone and just, yeah. What I was supposed to do? Oh yes, derivatives. We are interested in derivatives of these things. So what is the derivative of the most basic one, which is ln x? So the derivative of ln x is 1 over x. And this is the one that you are memorizing as the base formula. We are going to expand on it just like e to the x. Oh, I guess all the Calc 2 story already took the toll. Nice, go to work. Now I'm going to test something. Since you just left the classroom, when you see this, just let me know that you saw it in person. Next class, at the beginning. Awesome. All right, let's take a look at the more general case, which means it's going to be ln of f of x. So you can have ln of sine x or whatever of that sort. So I'm going to say ln of f of x, which again the chain rule is going to kick in. Now this is what you should remember. Look, so easy, so easy. You put the division line, you put the function as is, and you put the derivative. Can't be any easier. I mean, it can with e to the x. This is the second easiest one. You copy function as is and you put its derivative upstairs. Done. And that's the one that you are supposed to know. Because that's the one that you're going to see most of the time. Just like e to the f of x. And there is one more, again, the most general case, which would be with any base. So we are using LOGA. So this would be if it starts, let's say, log base 7 of sine x, or something like that. So we start with the derivative of log, which is any base now, of f of x. Is going to be, again, the same thing. You copy the function as is in the denominator, you put the derivative of it in the numerator, and then you will multiply in denominator by ln of a. So that's the modification because it's not ln. You can prove all of these things easily, derive them. So that's the general case. Now I boxed all three of them because Chapter 5 and Calculus 2 are coming. When you go to Calculus 2, most of the integral and u substitutions you're going to do in Calc 2 will be this. You will have integral of du over u, which will, as a result, have ln u, which is just backwards this one. You will learn this actually in 4.9. You will learn it backwards, but you will use it in 5.5, only one section in this class, and then almost every other problem in Calc 2. Almost every other problem will have the integral version of this one. Extremely important. In this class, this particular class, so for your exam now and for your final exam, this is the most important thing because this is the most frequent one that shows up. And then this is the most general formula which crowns over both of these forms by simply, if you put this to e, you reduce it to this. If you put this to x at the same time, you reduce it to that. So that's the most general case. For this class, this is the form that you really must know. And then for your purposes of future education and Chapter 5, Section 5.5, this is the one that you need to know very well. Cool. So we took care of that. Now, examples. That's how it goes. Examples. What is the derivative of ln of 4x? So we are going to use this middle formula, right? The one boxed in red. Anyone? Yeah? 1 over x. So we are going to write 4x, which is, you will literally copy, guys, Control-C, Control-V, okay? That's what you're doing. Identical. And then its derivative on top, which is just 4. 4 and 4 cancel. We get 1 over x. Great. What is the derivative of ln cosine x? What happened?
Negative cosine.
It's not negative cotangent.
Negative tan.
Ah, negative tangent x. Yeah, see, the things when you write it out, it just makes sense. So you copy cosine x as is, the derivative of it is negative sine x that goes in the numerator, and we have negative tangent x, and there you go. Life is nice and beautiful. Now I really can't make this hard. However, how about ln of, let's put something interesting, like cosine x over x squared minus x plus 1. Sounds good to me.
Let's see. Young Padawan learners. Four other cool people inside come up with that problem. I'm not sure. Why are you sorry? There's no need to be sorry. The greatest thing that could ever happen. And then 5 minutes. Oh, that? Oh, yeah, that's not good. Yeah, they're missing it. I wrote it down. I don't know. You stretched already or something? Yeah, random pain. I'll leave you with another minute or so to bake on this one.
Take it all time. Not so much.
If you're not using home, you use the phone. Set it equal to 0. For your 4.1. Oh, you have a question, right?
chose that route. Very brief part. All right, time is up. So do we all have the derivative? And what do we use? Really? Quotient rule? Really? Well, of course, it's a chain rule, the whole problem, because it's not ln x, but really? Quotient rule? Oh, I just want to see those face palms right now. I know, I mean, it's okay. It's fine. Yeah, this is why logs are so awesome. You have no idea. I'm just going to rewrite this problem as the derivative of ln cosine x minus ln of x squared minus x plus 1, because I know that algebra of logs, which I gave earlier as formulas, where the division in the algorithm goes into subtraction of logs, and then take two separate derivatives, which means cosine goes down, minus sine in the numerator, minus another fraction for the second one, x squared minus x plus 1 down, and 2x minus 1 on top, and I'm done. I just walk away. Like, drop the mic, right? I know. This motivates you to come back next time, right? For more awesome stuff like this. So see, this is what you can do. Next time you go out, this is what you write on a napkin, this problem. See if they can figure it out. It's going to be a chain rule and a product rule for like 30 minutes, right? You finish Nacho on your own. They're busy, right? And then you just show them the trick. No takers? You guys go out? You don't? Wow. Yeah, that's the reason. I mean, no one would invite me anymore, but yeah. Gotta love those people. Ah, what do you know? Woo. What do you know? Can take ln of 5 without calculator. All right. So yes, you are allowed to cheat. And by the way, with that being said, would you write this one as ln 4 plus ln x? ln 4 in a derivative would just be 0 because it's a constant, and then ln x is 1 over x, which is the answer? Yes, you would, right? Because now you know. You're awesome. You write this one as ln 4 plus ln x. ln 4 is just a constant. It's a number, right? You can calculate that in your calculator if you don't know what it is. And yeah. Awesome. All right. So now, the grand finale. Logarithmic differentiation. So let's come up with something. I don't know, whatever. What is the derivative of a cube root of x plus 3 times x cubed minus 5x squared plus 8 to the 7th power divided by something? How about x cosine x? Sounds good? Want to pepper in some powers there as well? Which one? On x or cosine x? Which one? Both power 17?
Like this power of the whole. Oh wait, that would just be it.
Yeah, exactly. Let's put the third power. Well, it doesn't matter really. All right, look at that. This is when you take, like you rip a paper outside of your notebook, right? And then you glue two papers together in landscape mode, and you have your first step done in that line, right? What do we have here? We have two product rules, right? And we have three chain rules, and all of that within a quotient rule, right? If you learn logarithmic differentiation, you will be able to take the derivative of this mentally without writing anything down and write that answer in a factored form and just walk away. And then any lesser problem, which is technically everything we did so far, will be much faster. So if you master this technique, you will be able to do that in a blink of the eye. And this is why I said you will be able to take in Calc 2, you take Calc 2, and there is a, I don't know, derivative for, let's say, the arc length or the surface area revolution or something. It has a derivative in the formula. As people are writing the functions down, you will be taking those derivatives mentally because it makes a joke out of differentiation. Now, just for fun, I'm going to write out the derivative for this, and then we're going to do much less convoluted examples to understand how is this done, and then we are going to use that technique on this one to see if I did it correct or not. But the derivative for this should be copy the same thing as is. So here we go. And then in the factored over here, we're going to have 1 over 3 x plus 3 plus 7 of 3x squared minus 10x divided by x cubed minus 5x squared plus 8. And then we should have minus 3 over x, and then we should have minus plus tangent x, and that should be the derivative in the factored simplified form. Now, if I made a mistake, then we'll fix it later. Let's check. So this is after you do all of the product rules and chain rules and quotient rule, which is actually the main one, right? After you do all of those, this would be the derivative of the entire thing. And as you can see, it is already factored. There's nothing else that you can factor out. Let's see how this is done. So let's do a simpler example. So let's start with find the derivative of x squared times the square root of x plus 7 divided by, I don't know, one function here, something, whatever, doesn't matter. Sine x, thank you, sine x. All right. So this would be a much simpler example, and we want to take the derivative of this. So it's called logarithmic differentiation, which means the log will play a big role in this. I'm going to write y equals x squared times square root of x plus 7 divided by sine x. And then I'm going to place ln on both sides. Once I place ln on both sides, I will differentiate in respect to x. So technically, I am taking the derivative right, of what I need to do. So I set the function to y, place ln on both sides, and look what's going to happen. What's going to happen is I'm going to solve this and then solve for dy dx, because I define y as the function that I need to take derivative of. So by looking for dy dx, I'm actually, by isolating dy dx, I'm actually figuring out this derivative. So on the left-hand side, we have the implicit differentiation, which means that on the left-hand side, I have 1 over y dy dx. But on the right-hand side, and here I'll do this in blood, I guess, I break this apart using the log rules and properties. So see, there is a multiplication, and multiplication of arguments goes into addition of logs. So this is ln x squared plus ln square root of x plus 7 plus minus ln of sine x. So all I use are those basic algebra properties for logs. Nothing special. I just expanded this. And you do these exercises in your pre-calculus class in section 3.3. I know you do it because I teach that class. So there you go. You have this, and then you are going to use the power rule to peel off these exponents. So you will have 2 ln x plus 1/2 ln x plus 7, and then you still have this minus ln sine x. That stays unchanged. So you are technically taking the derivative of this. But you know that as you are taking the derivative of this, the constants copy, and then you have ln x is 1 over x, plus copy the constant 1/2, copy the x plus 7, and then its derivative on top, minus copy the function downstairs, which is sine x, and its derivative up, which is cosine x. So look what you have. All you need to do is to move y to the other side. You're done. And y is all of this, which is the reason why when I did a complicated problem, I just copied the entire problem and then just came up with the parenthesis, which is this. All right, so what do? We write dy dx. We are moving y to this side. And now this parenthesis here is 2 over x plus 1 over 2 times x plus 7 minus the cotangent x. And just write in what the y is. Dy dx is equal to x squared square root of x plus 7 divided by sine x, and then times 2 over x plus 1 over 2x plus 7 minus cotangent x, and you're done. So we're going to do a few of these examples. Now, what you're seeing here is a lot of writing to show what is mathematically happening behind logarithmic differentiation. However, because I know at least you are going to be very interested in this, what's actually happening here is that all of this stuff over here, the only important thing is this. If you are able to mentally come up with this from there, that's all you need. Because I already told you, when to write out the derivative for anything, you copy the function as is, and you just have to come up with that part. If you're able to do that part mentally, which is algebra, the rest is a joke. Because look, 2 and derivative of x, ln x is 1 over x, so 2 over x. Boom, done. Over here, square root. I see square root, that's the exponent. If it's a positive exponent, it goes on top. If it's a fractional exponent, it goes on the bottom. So that's why it's 2 on the bottom. It's 1 over x plus 7. And then sine x, it's a negative because it's division here, so it's negative. So negative term, sine x goes downstairs, cosine goes on top. So cosine over sine is cotangent, negative cotangent. If you are able to mentally come up with this without any mistakes, the log derivatives are extremely easy. It's 1 over this, right? Or derivative over the function. So going back to the difficult example, you see the same behavior. All I did is in my head, I go, that's 1/3 coefficient, that's a times 7 coefficient, that's times 3 coefficient, and this one has no exponent, so no coefficient. These two are in the numerator, so positive term, and these two are in the denominator, both negative. Now this came from, remember the negative from the sign, so it should be negative, but double sign, double negative makes positive. So whatever is on top gets a positive sign, whatever is on the bottom gets a negative unless it's ruined by something. And then all I said is this, copy the function as is, and then 1/3 ln of this goes on the bottom and its derivative on top, but this derivative is 1. So I have 1/3 over 1 over x plus 3. Moving to the next one. Now this one will have stuff on top because it's not x plus 3. So this goes on the bottom as is. So I have 7 times, this goes on the bottom, and on the top is 3x squared minus 5 times 2 is 10x. There it is. Divided by itself. Because the derivative of ln is always derivative over the function. It's a pattern. If you are able to decompose this through logs, now, many of you are confused as hell right now because you know calculus, I have no issue with that. Because you are still struggling with the most basic formula of logs. If you want to learn this technique, forget about calculus, forget about derivatives, you know that. Don't waste time on that. You go into a pre-calculus book and practice as maniacs decomposing it. Do those problems in pre-calculus book where it says expand this expression. You spend an hour or 2 or 3 hours on that. And the rest of this is going to take you 5 or 10 minutes. That's how you learn this. So you spend time on actually what is needed to decompose this. Because if you are mentally able to decompose this, you don't have to write anything. Just write the answer every single time. You need to know what to study first, of course. So this is not something that you learn in calculus. As you can see, this is pre-calculus, knowing those 3 formulas that I gave you. Log of x times y, x divided by y, and x to the p. And this is your p over here. As the 1/3 coming out, p as 7 going in front, 3. Now this one is tricky because, right, this is 3 as a, but it cancels, right, because of the derivatives, how derivatives work. So, oh no, that one is wrong. That one is, wait. I think that one is actually wrong. I think that one is wrong because it will be 3 ln x. So it's just 3 over x. Oh no, I got it right. What the hell I'm talking about? I got it right. I almost corrected myself. That's very. I know. Imagine if I could get. All right, I'm not at that stage yet. Long time to do. Before ISM. Okay, what is that reference to? Ascension.
Bible, I guess. Movie, book,
No. It's a TV show.
If you really look into it.
It went for 10 seasons, and then they make another 5, and then they make another 2. No? Fox had only 1 season, which is epic, and that is the biggest fail of the universe that they didn't continue. Firefly, yeah.
No, it didn't even get a full season. That's the fact. It got like half a season and then a movie.
Yeah.
And that's it.
Firefly is one of the best things I've ever done. Ascension, come on. Really? In the Calc 1 class? I said TV show. It had 10 seasons under one name, and then they changed the cast a little bit, but the old one was still appearing here and there. It had 5 seasons of that one. and then one more.
When
talking about something that has 17 seasons,
Hang
we
on,
don't walking there.
When was when was this?
Before you were born.
Okay, well there you
It
go.
started before you were born, but you went well after you were born. Stargate, there we go, thank you. Holy nightmare. So Stargate FG1 for 10 seasons, Planet for 5, and then Universe. All right. So yes, the ancients, they ascended. That's what I'm striving for. Ascension. Now I'm annoyed. I'm going. Fine. All right. That's logarithmic differentiation. You get to learn the logs, and then after that, everything is a joke. You come up with any problem. Let me go back to, I don't know, product and quotient rule. You burned. See, you burned on this problem. Look at that awful answer. Look at that awful answer. How about you... What happened?
Terrifying.
This is the problem that you did in quotient rule. This is in your notes.
No, I know.
But
It's terrifying.
I know. But when you know logarithmic differentiation, you just look at it and you say, oh, yeah, you just copy this times this, which is going to be 2x over x squared plus 1, plus, ln is going to kill this one, so you just have the derivative of 5x, which is 5, minus 3x squared minus 7 divided by this. And you're done. You just walk away. That's what the derivative is. And you gave it in a factored form. Look at this mess. How do you set this equal to 0? You don't, right? It's insane. You don't. So that is where the power of logarithmic differentiation is. Now let's do this example showing all of the steps for logarithmic differentiation. So we're supposed to take the derivative of x squared plus 1 times e to the 5x, everything divided by x cubed plus 7x squared, I believe, or maybe 7x and then plus 1. Let's go back and check. Minus 7x plus 1. Minus 7x plus 1. Okay. So this problem was done in the product rule quotient, and it's bad because you have a quotient rule to be the main, and then the product rule is in there. So you have to do the nested rules. Plus you had the chain rule within e to the 5x. So this is not hard. This is annoying. Right? This is an annoying question. It's a really annoying question. If you know the three formulas, there is no hard. It's just annoying to do. Because you have to be very careful not to drop anything, not to forget anything, keep track of what's what. But now, we upgrade. Y equals, now this is all the mathematics that is happening behind the curtain. Those of you who want to learn how to do it mentally, you will spend considerable amount of time breaking this up. So we have ln of both sides, and then we differentiate everything. Now, the first order of business is to decompose this, which is going to be ln of x squared plus 1. Keep in mind that x squared plus 1 cannot be broken apart. And then you have ln e to the 5x. These guys cancel. Sorry, plus. And then you have minus ln of x cubed minus 7x plus 1. So when you have this, you just take the derivative of each one individually. All right, so 1 over y, that's the derivative of ln y, is 1 over y. dy dx is equal to Oops, that's too long. We copy the problem as is, x squared plus 1 times e to the 5x. That's the y. Oh, no, sorry. We'll copy the y later. We take the derivative here. I'm not used to writing all the steps. I gotta slow down. So let me reboot. I'm gonna reboot and redo the line so it's coherent, all right? I was done with this problem 10 minutes ago. Gotta learn how to live in the past, I guess. All right. So we take the derivative of ln y, which is 1 over y dy dx. On the right-hand side, we have this to take the derivative of. So the derivative of ln x, any derivative, when you see ln, immediately copy the function downstairs as is and put its derivative in the numerator. Plus, well, ln and e cancel, leaving 5x behind. The derivative of 5x is just 5, as I promised. Minus another ln, so division line, we have x cubed minus 7x plus 1, and then its derivative on top, which is 3x squared minus 7. All that is left is to move the y to the right, which will leave dy dx alone, and plug in what the y is, which was the original function. So dy dx is, original function is x squared plus 1 times e to the 5x divided by x cubed minus 7x plus 1. That's the original function. Times the derivative that was there, so 2x as a chain, 2x squared plus 1 plus 5 minus 3x squared minus 7 divided by x cubed minus 7x plus 1. I hope you're not disappointed, but yeah, that's it. It is extremely. This is actually product rule, and a quotient rule slayer. Literally, there is no reason to know those rules if you know logarithmic differentiation like this. You have to know the chain rule still, right? Because you were taking the derivative of this, and then in the chain this goes upstairs. So you have to know chain rule is the most important one of all. But this one, with this trick of applying ln's to both sides, that completely annihilates the notion of product rule forever, because as you can see, there is also a trick like this for limits. Wait, not be me. Would you like to know more? Okay, which movie is that? Very good, getting closer. No and no. Yeah, that was a sci-fi movie. Plus 5 on next test.
What was the movie?
Starship Troopers, of course. I've seen every single movie that exists, okay? I don't waste time, guys.
The actor. It's like some action movie guy. The guy from Starship Troopers.
Oh yeah, that's the one thing that I will never know.
What?
Like the names of actors. That's completely irrelevant to me.
It's a really weird movie.
And I also hate watching the movies that have these, main characters like very famous people, because I associate character for the movie with the face of the person. So Anthony Hopkins will forever be Hannibal Lecter, and that's it. So I watched one of those math movies that was supposed to be a mathematician.
Oh,
Yeah, I watched that. The whole movie I was waiting for him to eat his daughter or
Oh
something.
yeah, he's a great actor. It's just
I
that
know,
role.
but I can't get him in any other role. That's the problem. If every actor is going to get one role, yeah, one role per face. That's how I go. So.
Well, that's what's so great about like typecasting certain actors. Like they'll always have that one role. Like Michael Cera always plays Michael Cera in all his roles. So he's pretty much the same character.
I know, but that's what I like. It's like Schwarzenegger being a Terminator and Conan. So I know they have living hell out of me. So yeah. Well, that's when I was like, the Conan is going here. Now he's in the future. I have to connect to that somehow.
Never seen this name before in my life. Casper Van. What?
Schwarzenegger?
No, Casper Van Dien was the guy from Starship Troopers.
How do you feel about different actors playing the same role?
Yeah.
Like the Joker.
Okay, the Joker, that's okay.
Yeah, but
because
that's
he changes.
Jack Nicholson is the Joker. That's it.
No, Heath Ledger, man.
Oh, he died. Don't care. That doesn't matter.
Heath Ledger and Mark Hamill are always going to be the Joker. Especially Mark Hamill. I love Mark Hamill.
That people don't matter anymore.
Mark Hamill's not dead. Mark
No,
Hamill's not dead.
I was talking about
Heath Ledger.
Yeah.
Definitely outperformed everybody.
Yeah.
He did. I think he did a better job than Nicholson. I mean, Nicholson was great, but...
Maybe, but still, you know, some old wounds never heal. Okay. That was a little bit on film. I'll be in charge in calculus class. Are we done? We're done, right? You want another example? I heard, yeah, sure, and that always overrules. No.
One, yeah, sure.
Yeah, that always overrules. So let's pick up one from the book, which they think it's a good idea for you to use this type of differentiation. Awesome. Look at that. They're asking you to find the derivative of sine x raised to the tangent x. All right, 28 seconds. Set it equal to y, break it apart, do things, and be done with it. And then you allocate the for those people who know geography, they know that North America is not at all Australia. This needs to be
Oh, this could be a quiz for you. See now Indonesia is I tick all 1,000 islands. Oh, you don't want me to be done. It's really me.
I mean, it's not unjustified, but it is. Brazil.
Almighty, yeah. Almighty,
Doesn't matter.
I can very much worse with this less sensitive.
Yeah.
This is the 1% that makes it. So go figure the rest. Okay, so now I have to hold on.
Okay, let's take a look at this problem together. I saw some of you put an honest effort. So the first, what we do is we write it as y equals sine x raised to the tangent x. And then we are going to put, what just happened? Why did this pass? We're going to put ln on both sides and then differentiate. So now the exponent will go in front of the ln, and what we have is actually a product rule then. So we have 1 over y dy dx is equal to, and as I usually do, this is going to be tangent x times ln of sine x. So what do we get? We get the derivative of this is a product rule, so copy the first one, tan x, times the derivative of the second, it's ln, so we put sine x, and derivative of sine is cosine x top, plus ln sine x times the derivative of tangent is, very good. So now we need to move y to the other side. I have dy dx is equal to, And then the function itself was sine x raised to the tangent x, so that's the y part. All right, so now cosine over sine is, which is 1 over tangent, which means these two guys cancel out. What do they leave behind? 1. Plus, we have ln x, so we have a secant squared x times ln sine x. And that's it. Would you agree? Is this correct? Yes? All right. Let's hit the break. We'll restart the stream after we're done.